All right, hey everyone. In our last video, we basically implemented this linked list class with two methods. The two methods are append left, which creates a new node and adds it as the front or the head of the linked list, and then a print function to just print out the values inside of the list. In this episode, I want to just make a little bit of some refactoring changes. There was a viewer that commented and mentioned something that I kind of overlooked. And then I also want to talk about smart pointers and how we can modify our code to, instead of using raw pointers, we want to use smart pointers because that's kind of the modern standard in C++. It should make our memory management much easier or simpler. So the first thing I'll do is actually just kind of demonstrate the behavior of this currently. So in our main function, we are just creating an empty linked list called list. We are calling our append left method 3 times, which is basically adding these values to the front of the list. So by the end of the third one, we have 5 pointing to 15, pointing to 10, and then null as our tail. And then finally, we are printing out the values. So if we run this program, oops, I haven't recompiled it. So there we go. Now this spits out the output that we expect: 5 pointing to 15, pointing to 10, and then null. So yeah, the first, so actually, first of all, I'm going to just copy and paste all of this into a new file that we're calling smart pointer. And let me move to that directory. Okay, so this is just a new file, so we can make some changes. And the first thing I wanted to point out, or that the commenter from last video pointed out, was here, actually, when I was doing my code review with using Gemini, it mentioned that this function was a little bit weird. And let me explain what's going on here. So in our function, we're basically creating a new list node, and we're setting its value to whatever we pass in. And then we're setting its next pointer to point at null. And then in the next line, we're actually manually setting its next pointer to become the current head of our list. And then we're setting head to point at this new node. So this is, I think, a little bit redundant because in our constructor for list node, instead of having to pass in null pointer, we can literally just pass in the current head pointer, and the new node that we create will be pointing to the head of the list. So I can draw an example of what that looks like. Basically, if we have a list that looks like this, what we're currently doing is we're creating a new node with a value like 5, and we're setting it to point to null. And then in the next step, we're wiping this out and then making this point at 10 instead to give us a list that looks like 5, 10, and null after we update the head pointer. But instead of doing this, I think what we want to be doing is we'll have a list that looks like this. And when we create so we also have a head pointer that's pointing to the head of our list. But when we create our new value or new node that we want to store, instead of setting this one equal to null first, we can literally just set it equal to head and then update head to point at this. So it doesn't really make a difference in performance, I think, but it's just syntactically maybe more elegant. So the way that we can do that is, so here, instead of setting this new node to equal null pointer, we can set it to the current value of our head pointer. And then let's see, we can, instead of this portion here, we can actually just immediately update the value of our head pointer to become the pointer to this new node that we're creating. So hopefully this makes sense. Since head pointer is already a pointer, we can set it equal to whatever this statement returns, which is a pointer to our new list node, which we want to be the head. And since this is evaluated like first before this happens, it's fine to pass in head pointer here because this will be set after this is created. So hopefully that makes sense. And I think this is just a better way of representing what we're doing here. So we can also compile this code and just test that it still behaves the same as we expect. So output smart pointer, then we want to run smart pointer. And it looks like it still works. Okay, so that's cool. And I think the next thing I want to talk about is how we actually use smart pointers in this implementation so that we don't have to be dealing with these raw pointers and also all of this complicated, semi-complicated destructor logic. So smart pointers are included in the memory module or library, I guess you can call it. And specifically, what we're going to be using today is what's called a unique pointer. And a unique pointer basically has only one owner, I guess, in whatever context that you're using it in. So it knows that when it's done being used, it can immediately free that memory. You guys can probably Google a better explanation for that. But the way that we're going to do it here is we're going to look through our code and check out the places where we're using these raw pointers. And instead of using a raw pointer, we're going to use a standard unique pointer. And we have to give it a type. So it's going to be a pointer of type list node. And that's basically all we need to do. So we're changing this raw pointer to become a smart pointer. The name will stay the same, next pointer. And I'm not exactly sure if we need to explicitly initialize it to null. I think it should be handled automatically, but it may be best practice. I'm not really sure. I'm going to keep it as being initialized to null first. And we can do the same thing here for when we define our head pointer variable. We're going to change this part to be a smart pointer, all right, unique pointer of type list node. And same thing, we're going to keep this initialized to null. And for our destructor here, we actually don't need any of this logic anymore since our smart pointer should be taking care of freeing the memory for us. So we can actually just delete all of this. And I think another little bit of refactoring is, since these constructors are both empty, I think it is a convention to just call them default, meaning they're using the default constructor and destructor that should be created when we initialize an object. And then finally, I think we need to refactor this part here. So we're going to use another function that's actually called makeUnique. And what makeUnique does is kind of the same. You can think of it as a replacement for this new keyword. So it's going to make a unique pointer. And the way it's done is like this. We use standard makeUnique. We'll give it a type of list node. And then I think this part for now will stay the same, but actually we need to change this part here. And what's happening here is, so we're doing the same thing as before, but actually since this head pointer is a unique pointer already, we're not actually allowed to pass this into another function because of the fact that it's a unique pointer. It can't change ownership. So the way that this is actually handled is with the function or method called move. And we'll wrap this head pointer in this method. And basically what this does is it allows us to change the owner of this head pointer to become, I guess, handled by the constructor that we're passing it into, which is the list node constructor. So hopefully that makes sense. And hopefully I didn't make a mistake in my explanation, but that's the way I understand it right now. And I believe the last thing we need to change here is under our print method. We are actually going to need to use a .get And what .get does is it gets the pointer without taking ownership of it in this context. Since this is a read-only constant function, we're not doing anything. We're just going to basically read what's in this head pointer variable. I think we also need to change that here to .get. And hopefully, if I've done everything correctly, this code should still compile. So we'll run our recompile and run, and I get some errors. I believe I forgot to fix this definition here. So in our constructor for node, since we changed this to be a smart pointer, we actually needed to change this type that we're passing in to be a unique pointer as well. Let's see. Oh, same thing here. I think I missed this part. Next pointer also needs to be using a move, a call to move. All right, let's see if this compiles now. Yep, perfect. So we get our same expected output of 5, 15, and 10. And yeah, let me maybe just run this through Gemini and see if there's any comments from Gemini. Does this correctly implement linked list using smart pointers? So it says, this is a much more modern C++ approach. Using unique pointers significantly improves safety by automating memory management and preventing accidental shallow copies. There is a critical hidden danger using unique pointer for linked lists. So recursive destructor problem. While your code looks clean, it contains a potential stack overflow risk. Because each unique pointer owns the next one, destroying head pointer triggers a chain reaction. Head pointer is destroyed, which calls the destructor of the first list node. That destructor destroys its next, which calls the destructor of the second node. This continues recursively until the end of the list. So if your list is very long, this deep recursion will exhaust the program's stack space and cause a crash. Even with smart pointers, a proper implementation should define a manual destructor to delete nodes iteratively. Okay, so I guess this is an issue for super large lists. And it says we still might need to have a manual destructor. So what that looks like is here, instead of having our destructor for linked list to be default, we want to change it to be manual, I guess. So let's just copy this into here, and I'll take a look at the implementation. So it says while head pointer, move the next pointer out to take ownership, effectively dropping the current head without recursion. So head pointer equals standard move head pointer to head pointer's next pointer. Okay, so let's see if this compiles as well. Looks like it still works. Let's see if there's any other comments. Eliminate new and delete. Concise refactoring of this append left method. Raw pointer usage. Using curry equals head pointer.get in the print function exactly the right way to observe a list without taking ownership. Move semantics. Since you are using smart pointers, you have correctly identified that standard move is required to transfer ownership. So this is correct for small lists before that destructor implementation. But for this, I guess Gemini is recommending for a more robust implementation, we would want to have that iterative destructor instead of using a recursive destructor. All right, awesome. So I think that's it for this video. It's a little bit of a look into smart pointers. I guess there's probably, it looks like there's a lot more to learn, which seems to be the pattern for C++. There's a lot more the deeper you dig into it, and there's a lot of ways to do the same thing. But I think, yeah, basically by the end of this video, I'm kind of just taking a look at our implementation here, and I think We've learned a lot in pretty short amount of time, because I guess a week ago I didn't even really know how to make initialize values in C++. So I think we're making good progress. And as always, thanks everyone for watching. If you guys have any ideas for series or next videos you guys want to see, let me know in the comments. And yeah, see you next video.